before starting on what I said I would do today, I thought I would quickly try to tell you what I was trying to hurriedly say at the end of last lecture, to kind of tie the loose end of the spectral theorem discussion. So, okay, so what did we say? We proved that at least for self-adjoint A, with spectrum A, let's say, contained in sigma, it is a compact set in C. What we proved was that there is a unitary operator there exist, I should say, probability measures mu n on sigma and unitary u such that ua u star with self-adjoint minus 2 is contained in R. So that ua u star is equal to direct sum on n pi mu n of, I'll let t rather than z, so t is the identity function. So A is unitarily equal to direct sum of these guys, and we saw that in fact for each n the spectrum of pi mu f we wrote down what it was. Is all those in fact lambda and r such that pi mu so that mu n of the set of all z such that mod z minus lambda less than epsilon. What do you want to say? The spectrum means for each epsilon this is positive. That is for each mu n, for each n the spectrum of pi mu n f mu n of set of all z such that f of z minus lambda less than epsilon. This is f of z. Sorry for the mess. And and the norm of mu in there. Mu n L infinity mu n. And this is what we had shown last time. Right? The norm of that thing is exactly this quantity, and hence if you look at for all f in C sigma, and so norm of, what should I call it, direct sum pi mu n f So what is this? This is going to be the soup over n of norm f on in L infinity mu n. Now if you think of what this means, see, for each n, what is the norm f will be the inf of all those constants, whatever it is. But in fact, the one exercise we had seen in the magic theory class, that in fact you will find one null set you can throw out, outside of which the supremum is exactly this L infinity norm. Because by using countability of the countability of the measure. Countable union of null sets is null. So for each n you can throw away one null set, outside which the soup is exactly this quantity. So if you want to take the soup of all of this, you must for one of them you will take the soup outside that one bad set. So for the next one it will be soup outside another bad set. So you take the soup outside all the bad sets. No, union. You will be. So this is okay. Let me just say this is the next stage. I want to say this is the same as norm f L infinity mu, where mu is any measure such that mu n is absolutely continuous with respect to mu for all n. That means the null sets of mu are those which are null sets for all mu n. Example, you can take mu equal to any converging sequence, weighted sequence, average of mu n. You can take such a measure and you see that the norm, the L infinity mu. So what you've seen is, by magic, given this operator A, self-adjoint operator A on this separable Hilbert space, one has out of thin air pulled out a measure mu. In fact, there will be several such measures, but they must have this property, such that for every so that you apply it to T, so what am I trying to say? See, this is the so-called this f going to f going to f of a, which by definition is going to be, so this direction is going to be an operator here. Can you see my hand? The direction is an operator on this direction of the L2 spaces. So if I pull them back to H, then I'll get, that is what I want to call f of a. So we want to pull them back here, so I will say U star direction pi mu n f U. That is what you would want to call f of a. That is, if you take the function f to be f of t equals t, then what you get will be just a. A will be exactly the u star direct sum pi mu n t u. And this holds for every continuous function is what you've seen. And so what this shows for you is that C stars, in fact, this will say that the spectrum of A is in fact what you would call the support of that measure mu. By the support of a measure, you mean the smallest compact set outside which it has zero measure. And we've seen that f going to f of a, if I define f by that f of a with that u star direct sum pi mu n u that I had there, this for f in C sigma this is a nice move. In fact, isometric isomorphism. This is what. So I won't go into the details. So you can many of the things that I say, which I don't give details for, I'll give you one blanket reference at the end of this little thing. So in fact, this is the so-called, at this level, this is the so-called continuous functional calculus. So in some sense, elements of this generated C-star algebra you can think of as some kind of functions of A, which you can manipulate exactly as you do real functions. And by the bounded convergence trick, then that this extends to isomorphism from, in fact, L infinity mu to W star. Go to which is appropriately continuous. There is, it converts things which are converge according as in bounded convergence, almost everywhere convergence, uniformly bounded functions. The corresponding images will converge the strong operator topology. Okay, so this proves pretty much the kind of thing that I said in the first lecture, except that I haven't said anything about the multiplicity function. So to do for the multiplicity function, you have to do just a little bit more work. So one has to show that okay, so let me leave it there. I just say many of these details and many other things that I'm going to be talking about now, I will say that as a reference you can see the book of mine called Functional Analysis. By me, and in fact you can find you can download this from my home page. Okay, on my home page. So importantly, you look at chapter 3, which is where I talk about C-star algebras, where this whole thing is built up. Okay, so now let me move to the things that I was supposed to start talking about. Okay. So before I start embarking on the Statila Hida book, I will kind of gently let you into the thing by first mentioning a few things about topological vector spaces and the kind of thing that we need to talk about in things where they are not Banach spaces but vector spaces which are topological spaces. So first, for that, the first thing I mentioned this again earlier, I want to discuss need for nets. That is, these are substitutes for sequences. When you want to prove theorems about metric spaces, you do them using sequences. You want to prove that something is compact, then you prove that every sequence has a convergent subsequence. You want to prove a function is continuous, you prove that it maps convergent sequences to convergent sequences and so on. The problem with that in general topological spaces, sequences are not enough. Won't do. Meaning they are not enough. Well, so, for example, the most trivial example is you look at the so-called co-countable topology. The bad word. What I mean by this is the following thing. You take a set X, for example, the real length. You take an uncountable set, and you declare that the only open sets, I am going to describe the topology. So I want to say the only open sets are the empty set and co-countable sets, meaning sets whose complements are countable. Okay, only if a set is the only non-empty sets which are open are the ones whose complements are countable. Or equivalently, the only closed sets are the whole space and countable sets. Now it is easy to see that countable sets are closed under finite unions, under arbitrary intersection, and so this does give you a topology. Okay? And you can see that in this topological spaces, what are the convergence sequences? When will a sequence xn converge to a point x? So I say that because the complement of that entire sequence is an open set, right? Consequently, you think about it for a moment, you will see that the only convergence sequences are eventually constant. So what does, suppose the sequence xn wants to converge to an x, then if I take x and I take the complement of x, that is what, what should I say? Okay, so I take any subcollection of that sequence which does not contain the point x. The sequence might have x periodically. You remove all the x's from there. Take all the other points in that sequence. Now that sole set will be a countable set. The complement of that is the neighborhood of x. So for it to converge to x, after some point everything in your sequence must be in that set, which will mean that really that everything after a point must be equal to x. So in other words, if you take a sequence which is not eventually constant, then its complement will be a closed set, and here so not its complement. You take any sequence which is not eventually constant, take the set of its points, that will be a closed set. And by definition, there is a sequence in the closed set. If it wants to converge at all, it cannot converge to a point outside it, that set. So, on the other hand, the only closed set containing this set is the whole space. So there are points in the closure which are not limits of points from this dense set. So anyway, so whichever way you want to think about it, this will show that in general, if you want to discuss general topological spaces, sequences may not suffice. Now you might say this is an artificial kind of topological space, that you won't really run into this sort of thing in anything natural. But unfortunately you do, as you will see when you study these operator algebras. And so in order to handle this kind of thing, one needs to talk about nets. So let me make a few definitions. First, a directed set. See, usually what is a sequence? A sequence you read xn, where n are things in natural numbers. That's the sequence. A sequence in X is such a collection where all the xn's come from X and they are indexed by the integers. So now the only difference is the index set can be a more general ordered set, partially ordered set. So when you deal with many arguments with sequences, you would say after some point something good happens, after some other point something else good happens. So we go far enough, then both good things will happen. Okay? So the kind of thing that you will want to say is that you need a notion of this n will be replaced by a directed set. What is a directed set? That is, it is a partially ordered set. With the crucial property that for all alpha 1, alpha 2 in lambda, there exists an alpha 3 which is greater than both. This is the thing I was saying, that if you go beyond alpha 1, the first good thing happens. If you go beyond alpha 2, the second good thing happens. If you go beyond alpha 3, both good things will happen. Okay, so this such is a directed set, and the net is in X is just a function from a directed set into X. Okay, one usually writes or we'll just say X of alpha, alpha and alpha. Okay. So then many of the things that you do with sequences can be imitated and they work perfectly well here. Thus, for example, I want to talk about a convergent net. Do you want to say that now? Yeah, what would you mean by a net X alpha in a topological space X converges to an X So there's only one thing you can say to define it. How will you define this? So what you say mathematically, precisely. Usually for sequence you say if there exists an n, so that for all m bigger than n, and for every open neighborhood of that point you need to say something, right? So what is the correct formulation? For every open U containing X,
there exists lambda belongs to that predicate set such that for all alpha greater than equal to lambda, X alpha belongs to U.
and this is exactly what you do for sequences. And little exercise exactly as using that property of directed sets, that alpha 1, alpha 2, you show that if X is host of limits of convergent nets are unique. Is it clear what I mean? If X alpha converges, it means that the limit can only be one thing. You converge to X and to Y, then X has to be equal to Y. Why? Because if X is not equal to Y, you can find a U and a V which separate them, because in a host of space, by definition, if it converges to that point, then there is an alpha 1, so that after the alpha 1 you are in that open set, there is alpha 2, so that after alpha 2 you are in this open set. That means after alpha 3 you have to be in both open sets, which is not possible. Okay. So let me give you examples. The most probably some of the most important examples of directed sets that you would see. Okay. One. See, so when you have a topological vector space, we will want to make sense of some things like summation xi. Right? Some of a series or whatever. When you say series, you are thinking automatically index with integers. But in general, you might be interested in just where I is any set, you might be interested in sums like this. So how would you make sense of such a sum? So to do that, the one natural directed set that one can talk about is, so you are given a set I, then let me write f of I for collection of all finite subsets of I. I want to say this is a directed set in the natural sense. There is a natural order in this, with respect to which it is a partially ordered set, and with respect to which it is directed. What is the order? Just inclusive. Okay? So this is ordered by with respect to inclusion. because the union of two finite sets is finite. Okay. So what you will mean by saying that a family like this will be summable will be, you will define S of F for each F in I in F of I. Define S of F to be the sum corresponding to the terms in F. So it's just sum over xi, I in F. This makes sense. This will be a collection indexed by this directed set, so it is a net. It is a net in whichever vector topological vector space we are talking about. Okay. Now, I said summable, so this is summable. If the net star converges. What does that mean? That means to say it converges to some x means for every neighborhood, open neighborhood u of x, you must be able to find one finite f naught in fi, such that for every f bigger than f naught, S of f must be in that open set. All the partial sums beyond that f must be in f naught. There is one basic difference between the general considerations and sequences, which is the following thing. When you're dealing with sequences and n, there when you take any, you say there exists an n and n such that blah blah blah. The things before n there are only finitely many. So to say something converges equivalently, you will say in a metric space, give any open neighborhood that will contain all but finitely many members of the sequence. That is not necessarily true when you are dealing with nets. So before that lambda, there will be infinitely many fellows which are not bigger than lambda. So it is not true that convergent nets are bounded. The convergent sequences will be bounded. So which is one of the problems that you must be careful about when dealing with nets. Okay. So I'll discuss another very useful example of directed sets. So suppose X is a topological space. Then for any x and x, let n of x be a set of all neighborhoods of x. That means all those sets Usually one takes open neighborhood, but one doesn't have to take open. When I say neighborhood, I just mean some set which contains X inside its interior. So you say U is the neighborhood of X if X is an interior point to U. Take the collection of all neighborhoods of X. Okay. Then I want to say this is directed this is also directed by inclusion, as you said, but the interesting order for this net, a directed set, is the reverse inclusion. Because according to the reverse inclusion, as you go farther and farther down the directed set, you are getting smaller and smaller neighborhoods. So when I want to talk about things converging to X and so on, that is the direction I am interested in. Okay. So using this directed set, so proposition / exercise. So I'm not going to prove it. You have to sit down and prove it. So let A be a subset of X, topological space. Then I want to say the following are equivalent. A is closed. See, rather than a sequential description of being closed, I want to give the corresponding net description. So what do you expect it to be? It is the obvious thing. It is there if X alpha, what do you say, A alpha is a net in A, and A alpha which converges to some point X in X, then X in Y. It is closed under taking limits of convergent nets. And you will prove this using this net, this directed set. So many of these things are described so actually so see my book. I suggest that you look at the following things there. Section 2.2, we talk about nets. Section A.3, in there A.3.3 and 0.9. These are, like one of them will be this statement probably. Another one is a statement about continuity in terms of, in terms of preserving convergent nets. If you have map from F from one topological space X to another topological space Y, and F is continuous at little x in cap X, if and only if whenever x alpha is a net in X which converges to X, f of x alpha must converge to f of x in Y. And the way, and to prove that you would use this direct sense. So, okay, I have listed several things which might be pertinent to this or to what I'm going to talk about next, or section 1.6. Okay. Okay. So now I want to slowly and steadily move towards our goal. So we will be interested in these what are usually called locally So first of all, we want to look at topological vector spaces. So what is that? This is a vector space. It is also it also has a topology. And the two structures must be compatible. What that means is that the vector operations on X must be continuous. Then addition and scalar multiplication are continuous and viewed appropriately as maps from appropriate product spaces to appropriate ranges. They are continuous maps. Okay. And we will see one of these various things I said refer to 2.5, 1.6, various things I wrote down there. One of those things talks about one way of defining, getting examples of topological spaces. So, let me take this. So, suppose you have a set X. Suppose you have a whole collection yi are topological spaces. And suppose you have functions fi from x to yi. Then one thing you can do is, when we talk about topology, you want to look at things which are continuous. So you want to make X a topological space such that every Fi is continuous. Okay? That's easy. I can just declare that every set in X is open. If I give X the discrete topology, then every function from X is continuous. So that is being quite silly, there is nothing to do with the data. So I want to make X a topological space in as efficient a way as possible so that the FIs are continuous. So I want to put the least number of open sets I can on X, which will make all the FIs continuous. So how would that be continuous? So for example, all things of the form Fi inverse Ui Ui open in Yi they must all be open here. So you take this whole collection and you want all these things to be open in X. So you want this to be a subbase for the topology. That means a collection of sets is a subbase if they cover the whole space, and if it is the smallest topology which has all these sets as open sets. And to get the smallest topology, you must first take finite intersections of these, and then take arbitrary unions of those. So finite intersections of these will be a base for the topology. A base means arbitrary unions of those are open sets. So this will be a subbase for this. So let me just say tau of this collection is the topology I want. There is the smallest topology with this as subbase. Okay. That is how you make just sets without any topological structure. That is how you make them topological spaces if there are natural functions in topological spaces going around. Now I want to do the same thing. I want to get natural examples of topological vector spaces. And so there is the notion of tau of where this is a family of seminorms on it. What I'm trying to say is, I have a vector space X. I want to make this vector space a topological vector spaces, and I want the topology to be induced by. So here one says this topology is induced by these functions Fi. So I want the topology to be induced by a family of seminorms. So what does that mean? You know what is, have you all seen what a seminorm is? So it has everything except the definiteness property of norms. So okay, so what is this? F is a family of seminorms. Where each P is a seminorm. So I want all these. So what are these? So these are functions from x to r plus. Semi-norms are functions into 0 infinity. So I want to put a topology on f on x which makes every p continuous, and I also want it to be a vector space topology. There is addition and scalar multiplication to be continuous. So one of those exercises that I think if you see remark 1.6.5, which also alludes to exercise A.3.11. So I'm sure this A.3.11 is the one that discusses the topology induced by a family of functions. You want to use that to define a topology induced by a family of semi-norms. So this goes something like this. You define. See, not only should every p be continuous. So see XL. So I'm saying with respect to this topology, so in order for me to describe a topology, it's enough for me to describe what the convergent nets are, because convergent nets tell you what the closed sets are. Okay? So with respect to this topology, let x alpha will converge to x precisely when p of x alpha minus x converges to 0 for all p in F. Right. And these exercises will tell you how exactly one constructs the topology. Namely, for there is not a big. See, for each p and an x, if you look at a function f p x, it sends y to p of y minus x. You want all these functions to be continuous. So the topology, this topology, I want to say nothing but topology induced by all these functions f p x in x, p in f. But all this is a fancy language, so finally you'll verify things using this condition. That condition is the most usable and okay, so examples will be
why this shifting has been done? Why is that all semi-norms are continuous? And why that shifting has been done? Y minus x.
Otherwise, why is addition continuous? If I just demand p alpha to be continuous, that means x alpha converges to x means it is like in a norm space. You say that then norm x alpha converges to norm x. Don't say anything about when x alpha converges to x. See, typically we will be interested in our x will be b of h really. So I want to define semi-norms here. So for each or it can even be p of h k. You have two different Hilbert spaces h and k. So I can look at px, pxi to be defined by norm xi, xi in h. For each xi in h, I have one semi-norm. What does it mean to say x alpha converges to x with respect to this one semi-norm? That means that x alpha xi must converge to x xi. This is a strong thing, or if you want the weak thing, you can also look at semi-norms like this. Okay, we will be concerned with these, the topologies induced by these semi-norms. The topology induced by the first family of semi-norms is the strong operator topology. The second family of semi-norms induces the weak operator topology. Okay, so now let's start with the book. How should we start this next time? Next time? Huh? Okay, let's see what he says. See, and then we will be interested in, since we're talking about, it is like Banach spaces. In Banach spaces, okay, you have vector space and you have a norm. And then you will be looking at linear functions or linear operators which are continuous with respect to this topology, which you would like to translate to some kind of boundedness. Which is what you do in the norm case. So here also, given a family, okay, so let me give you one little exercise. So suppose X is a vector space and F a family of semi-norms. Family of semi-norms. as above. Then I want to say suppose phi is a mapping from x to the scalars. And the x is given the topology is given the sigma tau f, the topology induced by that family of seminorms. So I want to say that phi, when is phi continuous? With respect to tau f on x and the natural topology on C. But when do you think this will happen? See, look at, so linear, let me say linear function. So first I want to say a linear functional, see, between two topological vector spaces. A linear map will be continuous precisely when it is continuous at the origin. Exactly as before, you can just translate everything. In a topological vector space, all translations are homeomorphisms. Consequently, in order to check continuity, it's in order to check continuity at 0. If and only if we are continuous at 0, what does that mean? At 0, it means x alpha converges to 0 means p x alpha must go to 0 for all p. And it is that is a subbase for the topology. You take finite intersection of those for a basic neighborhood, that means finitely many of those things would only be involved. So it is equal to saying there exists P1, Pk in F such that some constant terms. There exists a constant. And so, no, okay, I think I'll leave it here. There's enough. I think you should do all these exercises to really get a feeling for the arguments that are going to be involved in various things here. So get used to the idea of these topological vector spaces and functionals on them and their continuity, how you check their continuity and so on. So another thing I want to say, because of this, see, I can make this, given a family of seminorms, I can make it larger. set of all finite sums. Some of them may even be the same. That is, I'm saying you take the cone generated by those p's. Take all possible integer linear combinations of those pk's. Each of those will be a seminorm. Now, if each of those initial pairs were continuous, then these will also be continuous. And the topology induced by these seminorms will be the same as these. Which means when you are dealing with a topology induced by a family of seminorms, you may as well assume that the family is closed under finite additions or multiplication by scalar also. You can even throw in a ck. Ca is a positive. Then both these families of seminorms will give you the same topology. So you might as well assume that if you are given a bunch of them, you can throw in all these additional ones. Okay, we'll start in earnest from next time.